Hello and welcome to this tutorial on the double integration method. In this tutorial, we are going to figure out how to find the deflection and slope curves for the whole beam for a simply supported beam under a UDL. Let's get on to it. Let's first take a look at the example we're about to solve. We'll consider a simply supported beam, AB, of uniform cross-section, carrying a uniformly distributed load with the intensity of W along the full span, which is L. The beam is supported by a pin at A and a roller at B, so the vertical deflection at both supports is 0, while the rotation is free. Our objective in this example is to determine three things: the equation of the slope along the beam, the equation of the elastic curve, and finally, the maximum deflection of the beam. This example will be solved using the double integration method, following the same systematic procedure we used in the previous tutorials. This slide summarizes the standard procedure for the double integration method. We assume that EI is constant within each segment of the beam. The process begins by sketching the elastic curve, taking into account the boundary conditions, 0 displacements at beam supports, and, if relevant for other examples, 0 displacement and 0 slope at fixed supports. We then use the method of sections to write the bending moment expression mx. If the loading is discontinuous, this is done separately for each segment. The moment expressions are integrated once to obtain the slope equation, and then that is integrated a second time to obtain the deflection expression, remembering to include constants of integration. Finally, we can evaluate these constants by using boundary and continuity conditions, and the resulting equations can be used to determine slope and deflection at any point along the beam. Here we begin the analysis by following the first two steps of the double integration procedure. First, we sketch the elastic curve. Since the beam is simply supported, the vertical deflection is 0 at both supports A and B. Under a uniformly distributed load, the deformation is symmetric, and the maximum deflection will occur at mid-span. We'll then move on to finding the bending moment equation. To do this, we'll introduce a coordinate x, which will measure from the left-hand support A along the span. Before we can find the moments, however, we do need to calculate the reaction forces. Now, if you've identified that this is a symmetrical beam, you'll see that the whole load WL needs to be divided by 2, because obviously the reactions also need to be symmetric. And therefore, AY and BY will both equal WL divided by 2. But let's follow through this with the equations, just in case you need to remember how to do that. We'll start by considering horizontal equilibrium, and since there are no horizontal loads acting on the beam, the horizontal reaction at support A is 0. Next, we take moments around A. For this, we need the reaction force at B, giving us, in our sign convention, a positive moment, times the lever arm L. Next, we figure out what the force is from the UDL. It is W times L. That gives us the whole force. And that needs to be timed the lever arm from the centroid of that shape, which in the case of WL is a rectangle, to point A, which in our case is L over 2. And the sum of that obviously equals 0, so we find that BY equals WL over 2. And finally, we apply vertical equilibrium. The sum of the vertical reactions must balance the total applied load, giving us AY plus BY minus WL equals 0. By substituting the value of BY, which is, as we just found, WL over 2, we find that AY equals WL over 2. So, as expected for a simply supported beam under a uniform load, the reactions are equal and the system is symmetric. Next, we construct the free body diagram, and we do that by removing the supports and replacing them with the reactions that we just found. Following that, we can find the bending moment, and we'll use the x as we defined previously, going from support A towards B. To do that, we consider a section cut at an arbitrary distance x from the left-hand support, and we note that x has to be between 0 and L. From the free body diagram of the cut section, we can see that we have the reaction at A, WL over 2, we have a portion over x of that UDL, and then at the end we will develop our internal reactions, so moment and shear. Obviously, in a general case, there'll also be axial load, but here we know that there are no horizontal loads. Taking moments around the cut section and setting the sum of moments equals to 0, we have M, and that is the moment, that internal moment that we've just exposed, minus the reaction force, WL over 2, times the distance x to the cut, and we also have the influence of the UDL, which gives us a positive moment, The force from the UDL is W times x, and the distance from the centroid of that small rectangular portion of the UDL is x over 2. And all that has to equal 0. If we isolate the moment, we get that the moment is WLx over 2 minus WLx squared over 2. This bending moment expression can now be used as the starting point for the double integration process. Here we carry out the two integrations required by the double integration method. First, we integrate the bending moment expression once to obtain the slope equation. For a beam with a constant EI, we substitute the expression from mx, integrate it term by term, and we get WLx squared over 4 minus WX cubed over 6, and not forgetting that first constant of integration, C1. We can then take that expression that we just got and integrate it. When we integrate it, we obtain the deflection equation. Carrying out this integration also introduces a second constant of integration, C2. So at this stage, our expression for EI times the deflection is WL x cubed over 12 minus WX to the power of 4 over 24 plus the first constant of integration, which has been integrated, so now we get C1 times x, plus the second constant of integration, C2. At this stage, we have the general expressions for the slope and deflection, both written in terms of the unknown constants, C1 and C2. These constants will be determined next using the boundary conditions at the supports. Let's therefore check what the boundary conditions will introduce into the equations. So for a simply supported beam, the vertical displacement at both pin supports is 0, and this gives us two boundary conditions. Y, the deflection, when x equals 0, has to be 0, and y, the deflection, when x equals L, so when we're at point B, at support B, also has to equal 0. These conditions are applied to the deflection expression that we just obtained from the second integration, and if we substitute them in, we can determine the two unknown constants of integration. So let's do that next. Starting with a boundary condition at the left support. The vertical deflection when x equals 0 and when we are at support A is 0. If we substitute x equals 0 into the deflection expression obtained from the second integration, which I've shown as the first thing on this slide, all terms involving x then vanish. And this immediately shows us that the constant C2 must be 0. With this boundary condition applied, the deflection expression is simplified, and it reduces to WLx cubed over 12 minus WX to the power of 4 over 24 plus C1 times x. Looking now at support B, here x equals L, so y when x equals L has to equal 0. Starting off with that reduced equation that we found on the previous slide, we'll then substitute x equals L, and that'll give us an equation in terms of the remaining constant C1. So here you can see that if I divide by L and rearrange, I can find C1, and the result is C1 equals minus WL cubed over 24. With this, both constants of integration have now been fully determined, and the slope and deflection expressions are completely defined. So let's look at those final expressions for slope and deflection. At the top, we have the final slope equation written in terms of EI theta or EI y tag. This results from substituting the constants of integration back into the slope equation we obtained from the first integration. And below that, we have the corresponding expression for the deflection, again written in terms of EI times y. At this stage, it is important to check the units. Each term in the expressions must be consistent, which provides a quick and effective check that the equations have been formed correctly. The deflection expression can also be rearranged into a more compact form, as shown on the bottom of the slide. This simplified form is mathematically equivalent and is often more convenient for evaluation and interpretation. Now we've managed to fully describe the slope and the elastic curve of the simply supported beam under a uniformly distributed load. We have been asked to determine the maximum deflection of the beam. From the symmetry of a simply supported beam under UDL, or uniformly distributed load, we know that the maximum deflection occurs at mid-span, where x equals L over 2. We substitute this value into the final deflection expression obtained previously, and carrying out the substitution and simplifying the terms leads to the expression shown here. The final result for the mid-span deflection is minus 5WL to the power of 4 over 384 EI, and the negative sign indicates that the deflection is downward, consistent with the direction of the applied load. Importantly, this result is written in parametric form, and this means that for any simply supported beam carrying a uniformly distributed load, the deflection can be evaluated directly once we know the material properties and geometry. So, provided we know the elastic modulus E, the second moment of area I, and the span L, and of course the load intensity W, we can calculate the deflection at any point on the beam using the full deflection equation. And we can also discover immediately what the deflection is at mid-span. And this number here, the 5WL to the power of 4 over 384 EI, is a number very much beloved by structural engineers. I hope this was helpful, and I hope it helped you see the procedure for the double integration method from start to finish for simply supported beam under a UDL. Join me next time for some more structural engineering.